Hello and welcome to this video about the nucleus. We are looking at the nucleus of an atom and we're going to review a little bit about nuclear structure, things we've learned about before, as well as look at nuclear forces. What is the strong force and how does that compare to the electric force? And we'll look at what radioactivity is. Remember what the atomic number is. It is the number of protons that an atom has. Here, if we look at these red little balls in the nucleus, and we think of those as being the protons, the atomic number for this atom would be 8 because there are 8 of those protons. And the atomic number determines what element it is. So 8 protons means this must be an oxygen atom. The atomic mass is the mass of that atom, and in this case, the mass is going to be 8 because there are 8 protons plus there are 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8. So this atom has a mass of 16 atomic mass units because remember, 1 atomic mass unit for each proton and 1 atomic mass unit for each neutron. Another way of thinking about it is that the atomic mass is simply equal to the total number of protons and neutrons in the nucleus. Subatomic particles, we're talking about those right now. Remember, electrons are in the outer shell. We are going to really be focusing on the nucleus, so we're not going to be talking about the electrons that are floating out there around. Remember, protons are a +1 charge and neutrons have no electrical charge. An isotope, if you'll recall, is an atom, two atoms that have differing atomic masses but the same atomic number. How would that be? Well, if it has the same atomic number, it would have to have the same number of protons. So an isotope would be an atom that has a different number of neutrons, therefore giving it a different mass. Keep in mind that this model here is definitely not to scale in a lot of ways. For one, if each proton and neutron have a mass of 1, and the electron is so tiny it's basically negligible, and we just consider it to have a mass of 0, this is not drawn to scale in that way. It's also not drawn to scale spatially. And what we mean by that is that the nucleus, the region outside the nucleus, is really, really large compared to the size of the nucleus itself. Mostly that atom is just space. In fact, the diameter of the entire atom is about 10,000 times greater than the diameter of its nucleus. If we think about blowing a single atom up, let's pretend we made it on to a scale of being having a diameter that's as wide as this football field is long. If we were to do that, the nucleus, we could put the nucleus in the very center and it would be the size of this little marble. And that would represent the model of an atom to scale with regard to the size of its nucleus versus the size of the entire atom altogether with all the electrons around it. So how does a nucleus possibly stay together? We've got protons that are definitely repelling each other because we learned, remember, that like repels like charges repel each other. So aren't those protons just dying to be far away? Yes, they are. The force that holds the protons and neutrons together is called the strong force. It is what causes the protons to be attracted to each other, the neutrons to be attracted to each other, and it is extremely short range. It is also extremely strong. In fact, it's 100 times stronger than the electromagnetic force. Here's just a diagram showing that the strong force is the force that causes protons to be attracted to protons, it causes neutrons to be attracted to neutrons, and it causes protons and neutrons also to be attracted to each other. Let's look at some of the forces at work in the nucleus and how distance affects them. If we look at 2 protons being very, very close together, we have the strong force acting on those. And it is a very great amount of force. It's a very large force as indicated by the size of these arrows, and it's attracting the protons to each other. We also have another force, the electric force. So these are each positively charged, so the electric force is a force that is repelling, so it is going to be acting to push those two away from each other. It is a smaller force than the strong force. Therefore, the net force is that the two protons would be attracted to each other to some degree. If, however, we put these protons a little bit further away from each other, they're too far apart to be attracted by the strong force, and so the strong force is equal to 0. There is no strong force at work because if we pull them apart a certain distance, the strong force is, remember, only a short-range force. The electric force will also be a little bit smaller because they are a distance away, but there will be some electric force that is repelling them from each other, pushing them in the opposite direction. So the net force in this case is going to be away from each other. As soon as these particles in the nucleus get any distance away from each other, the overall net force is going to be pushing them further away and repelling them from each other. Now let's take a look at how forces are acting in the nucleus when we compare different sizes of nuclei. Let's look at the strong force on a small nucleus. When we have a nucleus that only has a few protons and a few neutrons, they're all close enough to actually feel the strong force and be attracted to each other by this strong force. And since only a few protons are present, the total electric force repelling the protons from each other is going to be small. So here we have our net force that's pretty large that holds this nucleus together. What about a nucleus that has a lot of protons? Well, in this case, if we look at the strong force for any particular proton, it is going to be attracted to only the neighbors that are surrounding it. Remember, these will not have much effect as far as the strong force goes because they're too far away. So essentially, for a small nucleus or a large nucleus, the strong force is going to be the same, roughly, because it is what's holding them together and it's only short range. The electric force, however, in a large nucleus is a lot greater. We have a lot more protons with a repulsive electric force acting on them. And so there's a much greater electric force repelling these protons from each other. So the net force in a large nucleus that is holding it together is smaller. They are held less tightly than a nucleus that has fewer protons and neutrons. Another thing to look at when we're talking about different sizes of nuclei would be the neutron to proton ratio. And when we look at a small nucleus, an isotope is relatively stable when the ratio of protons to neutrons is about 1 to 1. In more massive elements, an isotope is stable when the ratio of neutrons to protons is about 3 to 2. So if a nucleus has too many neutrons compared to the number of protons, it will be unstable. But for a large nucleus, it has a higher neutron to proton ratio because the neutrons contribute to the attractive strong force, but they do not contribute to the repulsive electric force. So a larger nucleus is actually more stable with a greater ratio of neutrons to protons. So what is radioactivity? Well, in most nuclei, the strong force is strong enough to keep that nucleus permanently together. Those are stable nuclei. But when the strong force is not large enough to hold a nucleus tightly together, that nucleus can decay. And when a nucleus decays, it emits matter and energy. And that's what we call radioactivity. Radioactivity is the process of a nucleus decaying and emitting matter and energy. All nuclei that have more than 83 protons, by the way, bismuth has 83 protons, but all of them with more than 83 protons are radioactive, and you can see that in yellow. There are two others that are also radioactive that happen to be less than 83 protons. There are also some isotopes that have fewer than 83 protons, that are radioactive, like carbon-14. They just do not occur to any measurable degree, whereas all of these occur to very measurable degrees. Some advanced ideas. What are the four fundamental forces of nature? Or in 1949, Japanese scientist Hideki Yukawa received the Nobel Prize in Physics for his work on nuclear forces. What were his theories about forces? Or maybe you have some other ideas, other questions you'd like to investigate. I look forward to seeing what you come up with, and we'll see you in class.